first thing we need to talk about is what kind of units we're going to use in electricity. Our base unit for things electrical is to try and get a handle on how many electrons are present or how many electrons are moving past us at a given time. Usually when we try to quantify things, we use something like mass, for example. Or potentially we could use volume. We use mass and volume to quantify things, but they have their own usages. Those aren't just for quantifying things. They actually have a real meaning and a real purpose and come up in a lot of equations. For example, we can use volume to talk about how much of something we're buying or using. But volume is also an important parameter. It tells us how much room something takes up, not just how much of it there is. By the same token, mass, the real purpose of mass, such as in F equals ma, is to tell us how difficult it is to move something. But we use that as a way to talk about the quantity of something as well. If we go all the way back to thermo or maybe even chemistry, how do we quantify things in chemistry typically? By the number of individual atoms. So ways that we quantify things would be, N, the number of atoms present, M, how hard it is to move it, V, how much room it takes up, and these are ways that we quantify things. Well, for electricity, the sort of salient property in electricity is how much electrical wherewithal it has, and the sort of quantifying of things electrically is based on charge. The most basic unit of charge is the charge of a single electron, but kind of like N counting actual number of atoms isn't that convenient because the numbers end up so large. We tend to, instead of talking about, in this chemistry experiment, I used, 10 to the 85th sodium ions. We tend to use moles of something to quantify things when we use N, so we use a larger unit. By the same token, when we're doing charge, we'll tend to use a much larger unit called coulombs. Coulombs is the electrical effect, the charge, of a large number of, not atoms, but electrons. The charge of a single electron is 1.6 times 10 to the negative 19th coulombs, or 6.24 times 10 to the 18th electrons is how much it takes to build up one electrical charge, or 1 coulomb's worth of electrical charge. So coulomb operates a lot like moles. It says, well, here's a more convenient number for quantifying how much of this stuff we have. Like moles, one of the reasons we use mole, and the reason that Avogadro's number is what it is because that large number is how much it takes, is the number of atoms it takes to get us into more convenient units, in particular grams. So molecular weight is grams per mole. And so the number mole is what it is. They picked this huge number so that it would kind of get us from the atomic level all the way up to, normal mass units and that sort of thing. Well, Coulomb is done exactly the same way. So somebody came up with a gram at one point, and then they discovered atoms later, and then they had to adjust from like the atomic level to the, normal mass units. Same thing here. Somebody came up with an amp of current flow, and they decided that an amp, and this is one representation of it that they use in the book. Let me write this a better way. An amp is a coulomb per second. So somebody came up with an amp, and we already had a unit of time. So to quantify the electrical stuff, we said that a coulomb per second would be an amp, and so that we could use a 1 in front of all of these, that kind of established the definition of a coulomb. And then we kind of figured out how big an electron was, and we realized that there's, 10 to the 18th electrons make up 1 coulomb. So it all kind of came about a little backwards. That's how we end up with these large numbers. So one electron is a very small amount of a coulomb. A large number of electrons provide 1 coulomb's worth of charge, and a coulomb is the electrical effect of this large number of electrons.